I will talk about the low rank binary matrix approximation in column sum now. This is joint work with Fedor V. Fomin, Peter Golavach, and Kirill Simonov. And what is low rank matrix approximation? It's a method of compressing a matrix by reducing its dimension. It is a basic component in data analysis, including PCA, and it has many applications in many machine learning, scientific computing, etc. And what is this low rank matrix approximation problem? Here we are given a matrix of order m times n over the real field and a positive integer r, and the objective is to find a matrix B of same order but rank at most r, minimizing some matrix norm of A minus B. And two well-studied objective functions for low-rank matrix approximations are Frobenius norm and spectral norm. In the Frobenius norm, we have to minimize the value summation ij, summation going over I and j, and aij minus bij square. And in the case of spectral norm, it is like a minus b x, the L2 norm of a minus bx divided by the L2 norm of x. And for any non-zero x, the maximum value over x, such x. And the spectral norm, in some sense, the worst case extremal stretch of the matrix. On the other hand, Frobenius norm is an averaging measure. And both these problems are solvable in polynomial time using singular value decomposition. And we consider low rank matrix approximation of binary matrices over the field GF2, Galois field of 2. And so what is low rank matrix approximation over GF2? Here the input is a matrix A, which is a binary matrix of order m times n. And the objective is to find out a rank R matrix B, such that some matrix norm of A minus B is minimized. So when B has rank R, it can be written as C times D, where C is of order n times R and D is of order R times n. And the Frobenius norm in this case coincide with the L0 norm, entry-wise L0 norm, which is nothing but the Hamming distance between A and B, or the number of entries mismatching between A and B. And similar to the spectral norm, here we have column sum now. So we want to minimize the maximum over J, where J is the columns, and the Hamming distance between column J in A and column J in B. And this problem we call it as L1 rank R approximation over GF2. And what is known about low GF2 rank approximation, where we want to minimize the entry-wise L0 norm, that is the Hamming distance between A and B, where B has rank at most R. This problem is NP hard, and it is solved by two sets of authors independently in 2015. And the problem admits a p-task. In fact, it admits a e-p-task, a randomized linear time approximation scheme. And these approximation schemes are obtained by two sets of authors independently. And our result is about L1 rank R approximation over GF2. That is, we want to minimize the column sum now. That is, we want to find out a matrix B of rank at most R, such that the maximum over J, the Hamming distance between the column J, column vector, the jth column of A and the jth column of B should be minimized. A simple reduction from closest string shows that the problem is NP hard. And our main result is the following. This problem admits an approximation scheme, that is a randomized 1 plus epsilon approximation algorithm running in time, this quantity m to the order 1 and n to the order, which is a order of a function of r and epsilon. So I will give a very brief, I will give a proof overview here. Our proof has three major steps. In the first step, we reduce our matrix approximation problem to a kind of k-center problem, which we call it as binary constraint k-center. And then using dimension reduction technique, we reduce binary constraint k-center to a problem called binary constraint partition center. And in the final step, we solve this binary constraint partition center. So look at the, now I will give a brief idea of step one. That is, I want to reduce our problem, that is matrix approximation, where I want to minimize the column subnorm to binary constraint k-center. So for that, look at our problem. So we are given a matrix A and R, an integer, and we want a matrix B, which has rank at most R, and which is close to A, in the sense that for any column, for any jth column, the jth column of A, the Hamming distance between the jth column of A and the jth column of B should be minimized. And I want to minimize maximum over J such that the Hamming distance between column J of A and column J of B. And so here I could write, when B is rank R matrix, I can write B as sum of R rank 1 matrices, BIs. And when BI has rank 1, all non-zero columns of BI are identical. This implies that B has at most 2 to the R distinct columns. This implies that I can visualize this problem as follows. I want to find out these 2 to the R distinct columns. These are represented by the blue points here, and the red points represent the columns of A, such that the maximum distance of a red point to the closest blue point is minimized. Okay? And there is a relationship between these blue points, that is these 2 to the R, 2 to the R vectors which we found. And they should, the rank of those vectors should be at most R. And this problem, whatever I talked about here, can be defined like a k-center problem, which we call it binary constraint k-center. To define that problem, we need some definition. So let R1, R2, etc. up to Rm, they are k-array relations over the universe 0, 1. That is, each Ri is a set of tuples, is a set of k tuples, where each entry in a k tuple is either 0 or 1. And then we say that a set of centers C1, C2, etc. up to Ck, they are all vectors of length m, satisfies these set of k array relations R1 to Rm if for any I, the row I, for any I, think I as row I, C1 of I, C2 of I, etc. up to Ck of I, this will form a k tuple that belonging to Ri. So consider an example. When m is equal to 2 and k equal to 3, and consider R1 and R2 as mentioned here, then these vectors C1, C2, C3 satisfies these set of relations are the set of relations R1 and R2. Because look at the first row. First row contains 0, 0, 1, and that belongs to R1. And the second row is like 1, 0, 1, that belongs to R2. Now the binary constraint k-center problem is the following. Given a set of vectors of length m, and n vectors are given, and an integer k, and a set of KRE relations, M of them are given. And among the set of senders C1 to Ck satisfying R, find C minimizing the maximum distance of a vector x in X such that the maximum over x in X, the distance between X and C, that is the distance of X to the closest vector in C. That should be minimized. And how to reduce our problem to binary constraint case center. So the input is A and R. So what we want to partition A into 2 to the R parts, and we want to find the senders for each of these parts. And this should, the rank of these 2 to the R senders is at most R. And we want to minimize the maximum distance of a column to the closest center, of a column of A to the closest center. So how does the reduction work for R is equal to 2? I just take X to be the set of columns of A, and for any I in M, Ri is the following set of 2 to the R, which is equal to 4 tuple. Here K equal to 2 to the R. And the tuples are 0, 0, 0, 0, like 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0. If I look at the last entry here, that is a GF2 sum of first and second. So one can easily show that any set of senders, K senders, satisfying these relations, each Ri is same as this one, R1 is same as this set, R2 is same as this one, then that set of senders will have rank at most R. Moreover, for any set of senders satisfying this one, the rank is also at most R. And for any set of senders whose rank is at most R should satisfy this property. One can easily show that because the fourth entry is a sum of second and third. So we reduced our problem matrix, low rank matrix approximation, where our objective is to minimize column sum now of A minus B to binary constraint case sender. And now I will explain how to reduce this binary constraint case sender to another special, kind of a case sender problem, which is binary constraint partition sender. The binary constraint partition sender, the input is as follows: a set of vectors x and in integer k, and similarly a collection of k-array relation, and also a partition x1 to xk is given. And among the set of senders satisfying R, we want to find C minimizing the following quantity. So maximum over I going from 1 to k, x in xi, the Hamming distance between d, x, ci. So think that I want to compute senders for each of these xi's. And the distance is any vector from xi to the sender ci. And that should be minimized. So overall x in xi and I belonging to k. And now I will explain how to reduce BCC to BCPC, that is binary constraint case sender to binary constraint partition sender. So here the input for partition sender also contain a partition of x other than the instance of a BCC. So what we do is we apply the dimension reduction technique of Ostrowski and Rabbani. This says as follows: for any set of n plus k vectors of length m, binary vectors of length m, and epsilon greater than 0, there is a linear map y, linear map phi from y to 0, 1 to the power order log n. That is, I can map y to a small dimensional space such that the Hamming distances between any two vectors in psi of y are relatively preserved with high probability. So what we can think is, think y is equal to x union c, where c is a hypothetical center. Then for any vector x in x and c in c, the Hamming distance between psi x and psi c is relatively preserved with a high probability. And we can construct this psi like by applying the theorem of Ostrowski and Lebani. And then what we get is like, so psi we know how to compute psi of x. And we guess psi of c. I don't know c, but I will guess psi of c. And this will cost n to the order k by epsilon to the 4. Then what we do is, each vector in x will be put in the cluster xi if the closest sender in psi of c in from psi of small x is psi of ci. Then I will put that vertex x in the cluster I or cluster xi. So essentially, look at psi x and psi c. Psi c I guessed, psi x I know. Then I partition psi x based on which are the vector, based on which vectors are closest to which of these senders in psi of c. And then that partition of psi x actually can be pulled back as a partition of x. And that leads to a partition of x. Then one can show that any 1 plus epsilon approximate solution C prime of this new instance BCPC, that C prime is a 1 plus epsilon square approximate solution for the original instance of binary constraint K sender. And the proof follows from the fact that this is a dimension reduction where distances are preserved, relatively preserved. And so this is the way we could reduce binary constraint K sender to binary constraint partition sender. And once we reduce to that binary constraint partition sender, what we do is we formulate this problem, binary constraint partition sender, as an integer program. Then we solve binary constraint partition sender using randomized rounding. So we solve this LP and we will get some we solve this linear programming relaxation of this integer programming, and then we apply the randomized rounding technique to get an integer solution. And this method is similar to the one used for petas for closest string. And this is all about the proof technique or like proof idea I want to talk about. And then I will conclude my talk. In this paper, we gave a petas for L1 rank R approximation over GF2. That is, we are given a matrix A and I want to find out a matrix B of rank at most R such that the column sum norm of A minus B is minimized. And the running time is m to the order 1, n to the some function of r comma epsilon. Now it is natural to ask, can we get an e-petas, or in other words, can we get an algorithm with a running time f of epsilon into n times m to the power g of r, assuming r is a constant. Then if r is a constant, then this running time is an e-petas, right? But this is not possible by simple adaptation of a result on closest string by Saigon et al. We can prove that if such an algorithm exists even for r is equal to 1, then fpt equal to w1. So assuming fpt not equal to w1, we cannot get any petas for this problem. And in fact, we can prove that by adapting a similar result about closest string. Assuming exponential time hypothesis, we cannot even get an algorithm of running time f of epsilon times n to the little of 1 by epsilon, even for r is equal to 1. The open question I want to pose here is, can we get an algorithm of running time f of r comma epsilon and m times n to the power polynomial in 1 by epsilon? Notice that in our algorithm, the r is sitting in the exponent of n. So can we remove this r from this exponent and make it as a function of r and epsilon only, like as a factor here? And this question is open. And with this, my talk is complete. Thank you.